In this video, we have the definition of a derivative. Derivative refers to slope of some sort of a function at a particular point. Eventually, we're going to find how to do the derivative of just an equation because depending upon the complexity of the graph, your slope might change at all sorts of different points. So it'd be nice if rather than doing this over and over and over again at all these individual points, we could just find an equation that represents the slope, a slope equation, and then we just plug in the value. So we're getting there. All right, so before that though, we're just going to figure out what the slope is at a particular point. So we're going to be doing the limit as h approaches 0 of f of a plus h minus f of a divided by h. And that came from us finding the slope of the secant, which was y2 minus y1 divided by x2 minus x1, which then simplified. The a's canceled out. We got an h. And then the limit as h approaches 0 is how you get your tangent. That's taking this point and squeezing it tighter and closer and closer and closer, making it more of an instantaneous slope rather than some kind of guess. All right, so that's what we got going on. So we're going to apply that onto this problem. All right, so we're going to be finding the slope. Here's our function. We're going to compute the slope at 2. This is called f prime. So anytime you see that, that refers to slope. So f prime at 2, which is the slope at 2. And we're going to use that to find the tangent line, which basically means at the end of this, we're going to be creating our linear equation. And we're going to use this point slope formula for it. All right, so we're going to be finding the slope at 2, which means we're going to be doing the limit as h approaches 0. Right, so I'm just copying this verbatim. Our a value is 2. So we're going to be doing f at 2 plus h minus f at 2 divided by h. All right, so here's where this one's going to get a little messy. So we got to be careful with our algebra. So we're going to do in the limit as h approaches 0. F of 2 plus h. So that is what we're subbing in 2 plus h into. So it is the square root of 2 times 2 plus h. All right, so that's on the inside, and then plus 1 is on the outside. So that piece minus f at 2 would be us plugging 2 in. So 2 times 2 is 4. Square root of that is 2 plus 1 is 3, which I already knew that, right? That value was already given to me. So minus 3. So I put the parentheses on these things frequently because especially when we start to generalize the equation rather than an actual value, we're going to have some distribution that we're going to be doing. So I kind of have this, try to keep good habits as I go through it. So there's nothing to distribute here, so I really don't need it, but we'll need it on future ones. So limit as h approaches 0. In here, we have the square root of 4 plus 2h plus 1 minus the 3, so minus 2 over h. All right, so here's where the problem is. It's not a problem, we have to fix it. So at this point, we would be plugging in 0. And so if we plug in 0, we would have the square root of 4, which is 2 minus 2. We would get a 0 on the top. If we plug in 0, we get a 0 on the bottom. That is a hole. Well, the limit exists on a hole, which just means that we are going to have to do some manipulation. That manipulation, anything that involves a square root, is going to be multiplying by the conjugate. So 4 plus 2h plus 2. 4 plus 2h plus 2. All right, so what I won't do is distribute the bottom, but I will distribute the top. So if I multiply this square root times this square root, still have a limit as h approaches 0, is this just becomes 4 plus 2h, and then I would have a plus 2, right? 2 times 4 plus 2h, square root of that, and then minus that distribution, minus 2, square root of 4 plus 2h, and then a negative 2 and a positive 2, so minus 4. All over this undistributed 4 plus 2h plus 2. All right, so hopefully one last little step before we can plug in our zero and drop our limit. We're going to combine our like terms. These square roots cancel. They always do when you're multiplying your conjugate. Your perfect square kind of got rid of your square roots here. And that -4 cancels with that +4. So we're really just left with a 2h. So the limit h approaches 0. We have a 2h over h times 4 plus 2h is inside the square root plus a 2 on the outside the square root. All right. So we haven't really canceled anything top and bottom. So we still have this 0 over 0, but here's where these h's are kind of factored out. They can cancel each other, and now we don't have our limit problem. All right, so we're left with the limit as h approaches 0, and we just have a 2 on the top, so no chance to have a 0 on the top. And then we have a 4 plus 2h, and then plus 2 on the bottom. And because it's a plus, we're going to be okay. So if we plug in our 0, we have 0, we don't have anything to plug in on the top, so that's a 2 over square root of 4 plus 2 times 0 plus 2, 2 on the top. That just becomes a square root of 4. And we square root the 4 and get a 2 plus the 2, right? Originally, we had a minus in there, and so that would have made our 0, but now we don't have it because we manipulated our equation. And so we're looking at a 2/4, which is a 1/2. Ooh, so all that work was going to get us our slope of a half, which really we're not done. We're going to use that slope now to find our tangent line. So our tangent line was we needed that slope and we need a coordinate. So we have y minus 3 equals 1/2 x minus 2. We'll distribute y minus 3 equals 1/2 x minus 1, because we're distributing it a half. We'll add 3. Y equals 1/2 x plus 2. And that is the equation of our tangent line, and that is our slope that we needed to find that. So if I wanted to check this, I would graph this, plot this point. I would go into Desmos, graph that, plot that point, and then graph that line, and it should pass through that point and be tangent to that equation. Okay, so that was another example, this time of using the definition of a derivative at a point.